In this video, I want to show you a few examples on rationalizing the denominator. Before we talk about specific examples, I want to explain to you the difference between a rational number and an irrational number. I think the best way for you to understand this is to first explain what an irrational number is. They're opposite from each other, and so hopefully understanding irrational will help you better understand rational. So what I have here on the screen is that an irrational number are those never-ending, never-repeating decimals. A really popular one that you probably learned about in high school is the value of pi. When you're working with the area and circumference of a circle, pi is equal to the decimal 3.14, I think it's like 159, on and on and on and on. That's an irrational number because it never stops and it never repeats itself, so you can't put the bar over top of it to stop the repeating. Most radical expressions are irrational, okay? And so what I have down here is 8 examples of radical expressions. I actually want you to take your calculator out for a minute, or if you have your cell phone handy and you can access the calculator app. And all I want you to do is just type in, I want you to pause the screen and I want you to type in the decimal that you get for each of these numbers. And then we're going to go back and determine what makes a radical expression rational and what makes it irrational. Okay, these are the answers that I got when I typed these into the calculator, and I want you to notice how some of them produce these really long decimals and some of them produce whole numbers. These radicals that produced these long decimals, those are called irrational numbers. So let's compare those numbers, so the square root of 2, square root of 6, and so on. Compare it to letter C. Well, and I see that I have B and D over here. Compare it to these that I don't have a red box around. The square root of 9, square root of 25, and square root of 49. Each of those numbers, 9, 25, and 49, are called perfect square numbers. There's a whole long list of them. We've talked about this in class. It's 1, 4, 9, 16, 25, 36, 49, and on and on and on. And those radical expressions that are rational are when we take a square root of a perfect square number. And so the whole purpose of today's lesson is we are going to be working with fractions. And of course, fractions have denominators. And we want to create a situation where there's always a rational number left over in the denominator. So we do not want a radical symbol in the denominator. I'm going to walk you through a few examples. It's going to start off really easy and then gradually get harder. But hopefully this will help you understand the concept better. Okay, take a look at these 3 fractions. All 3 fractions have radicals in the denominator, but I want you to look more carefully at the radicals in each of these denominators. Do you recognize that 25, 100, and 9 are perfect square numbers? So each one of these we can easily replace with a whole number, and then we would rationalize the denominator. Okay, so for example, we can replace square root of 25 with 5, and so 3/5 is the answer because we rationalized the denominator. We took what was in the denominator and put a rational number there. Next, this is the square root of 2 over 10 because the square root of 100 is 10. Now we can't simplify this because the 2 is under the radical, the 10 is not under the radical, so we can't simplify this fraction, but we have rationalized the denominator. It's just the idea of removing the radical from the denominator and you have a rational number in its place. Next, we can replace the square root of 9 with 3. So this is 3 square root of 2 over 3. Now we can cancel these 3's because they're both outside of the radical. And so the final answer is just the square root of 2. It doesn't matter about the numerator. The numerator can have a radical or it can have a whole number. That part doesn't matter. The focus is all about the denominator and how to create a situation where we have a perfect square number in the denominator, or as you'll see in a couple slides, a perfect cubed number in the denominator. Okay, take a look at this problem. Okay, this problem is different than the ones that we just solved because 2 is not a perfect square number. All right, now if you remember from just working with fractions in general, if you had the fraction 2/3 and you wanted to change the denominator, let's say you were needing to add 2/3 to another fraction, do you remember how it was okay to do something like this, to multiply, let's say by a fraction 4/4, and then we would just multiply straight across, 2 times 4 is 8, and then we would multiply straight across the bottom to get 12. And this 8/12 is exactly the same value as 2/3 because the fraction that we multiplied by, 4/4, has a value of 1. We're going to take that same idea and we're going to work this problem out over here. We are going to multiply this fraction by another fraction that's going to have the value of 1. We specifically want to get rid of that radical, the square root of 2. Now think back to the prison breakout story that I've told you in class. If we had a prison, and remember we call the radical our prison, and if we had a single inmate with a number 2, how can that number 2 escape prison? Well, he has to have, or she, sorry about that, they have to have a second person that matches their number to escape, right? They have to have 2 2s. And then once there's 2 2s, they can escape in groups of 2 from the radical. So here's how we're going to set up this problem. We are going to multiply by the fraction square root of 2 over square root of 2. I strategically picked square root of 2 because I want this bottom radical to have 2 2s. Because I know I can take the square root of 2 2s. The numerator, again, numerator is not really a concern. We're just going to push those numbers together. The whole number 5 goes first, and then the square root of 2. And from our multiplying lesson, we know we can multiply square root of 2 times square root of 2, which is square root of 4. We also know that 4 is a perfect square number, so we can take this out to one more step. Numerator is staying the same, but we can switch out the square root of 4 for the value of 2, and that's your final answer. Again, we cannot cancel those 2's because 1 is under the radical and 1 is outside the radical. So 5 times the square root of 2 over 2 is the answer. Next, go ahead and write this problem down. It's the square root of 7 over the square root of 6. Again, we want to multiply by a radical. It's going to be radical over radical, focusing on how can that 6 escape jail. If you have a 6 in jail, the only way for that number to escape is if you have another 6. So that's what we're going to multiply by. We're going to multiply by the square root of 6 over the square root of 6. We can just multiply straight across. 7 times 6 is 42, and 6 times 6 is 36. We can go ahead and change out the square root of 36 for the whole number 6. And 42, even though it looks like a larger number, do you guys see that there's not any doubles there? So we are going to leave the square root of 42 in the numerator. It cannot simplify with the whole number 6. And so we have done our job. We have rationalized the denominator. We have taken the radical, and now we have a whole number in the denominator. Okay, these are gradually starting to get harder. Please write down this problem. Notice that this is the first time that there's a whole number already in the denominator. I want you to ignore that whole number for right now. Let's just focus on how to get rid of the radical x. So we're going to multiply by the square root over the square root, and then I'm going to ask you the same thing. If you had x in prison, you would need one more x for it to escape the prison. And so that's exactly what we're going to multiply by. We're going to multiply by the square root of x over the square root of x. Numerator would be 5 times the square root of 2x. Denominator would be 4 times the square root of x squared. However, the square root of x squared is simply x. So this is going to be 4x in the denominator. Numerator is going to stay the same. We cannot cancel the 5 and the 4. We cannot cancel the 2x and the 4x because the 2x is under the radical and the 4x is not. And so this is your final answer. Remember, this is all about taking a fraction that has a radical in the denominator and turning it into a fraction that does not have a radical in the denominator. Okay, I'm not really sure why it got small, but let's go ahead and work this problem. We're almost done. Okay, I've talked to you in class about how a big radical is the same as two small radicals, so we can put radical 10 over radical y. Same pattern's going to happen. We're going to multiply by the square root over the square root. Right now there's a single y in the radical. We need one more y to get rid of that radical. Numerator is going to be square root of 10y over the square root of y squared. Numerator is going to stay the same. Even if we did a factor tree of 10, 10 breaks down to 2 times 5, and there is not a double. And then the square root of y squared, remember that's y times y, and there's a double. And so you can put a single y in the denominator with no radical, and that's your final answer. Okay, these next, I think there's one more after this, maybe two more. These deal with cubed roots. And so remember, for a cubed root to escape, that we need 3 of the same number, right? We got to circle groups of 3. So we're going to multiply still by a radical. This time it's just going to be a cubed radical over a cubed radical. But I want you to think about, see if you can visualize this. Right now, underneath the cubed radical is a single 2. We know that we need 3 of the same number in order for that number to escape. Right now we have a single 2, so we need 2 more 2's. And how we represent that in math, 2 more 2's, is the number 4. So I want you to multiply by the cubed root of 4. The numerator is 5 cube roots of 4 over a cube root of 8, because 2 times 4 is 8. 5 cube roots of 4 cannot simplify, but we know this 8 is 2 times 2 times 2, and so we can just put the whole number 2 in the denominator. We cannot simplify the numerator any more than what it already is, and so there's your final answer. All right, take a look at this one. This is 2 over 5 cube roots of x. Again, I want you to ignore the 5 and just focus on how do we get rid of the cubed root of x. Okay, so I'm going to talk to you about the same process. If you have x in prison and x wanted to escape from jail, this is a cubed root problem, and so you have to have groups of 3 escaping. The only way for a single x to escape is if there were 2 more x's also locked up in prison. So that's exactly the situation we're going to create. We're going to multiply the numerator and the denominator by the cubed root of x squared. Remember that exponent just talks about how many x's we need. The numerator is 2 times the cubed root of x squared over 5 times the cube root of x cubed. Again, the 5 is okay. The 5 is a whole number, and so it's just going to stay put. But we know that this cubed root of x cubed simplifies to a single x. So our denominator is 5x, numerator is 2 cubed roots of x squared. We cannot do any further simplifying, and so that's your final answer. Okay, this is the last problem on this video. Again, like I've told you in class, a big radical is the same as 2 small radicals. So I want you to go ahead and separate this into 2 smaller radicals. Now we have the cubed root of 5 over the cubed root of 4y. So right now, that denominator, if we were to make a factor tree, it's 2 times 2 times y. My question to you is, because they have to escape in groups of 3, right now we only have 2 2's. Do you see that in order for the 2's to escape, we would need another 2? But what about the y's? There's only one y, and do you see that we would need to have 2 additional y's for everyone to escape this cubed radical? So that's exactly what we're going to multiply by. We are going to multiply by the cubed root of 2y squared. We're going to do that to the numerator and the denominator. The numerator is now the cubed root of 10y squared, and the denominator is now the cubed root of 8y cubed. Now if we go back down here, this is basically the factor tree of 8y cubed, and we have a group of 3 2's and we have a group of 3 y's because we specifically designed it that way. And so the final answer is the cubed root of 10y squared over 2y. If you have any questions, please contact me. You can message me, you can email me. I'd love to help you more with this topic. Have a great day.